Hello students, I am Dr. R. Krishna Kumari, Assistant Professor, Department of Mathematics, SRM Institute of Science and Technology, Katangulattur. Today I am going to share certain topics in multiple integrals. The outline of this module is initially we are going to see about what is meant by double integration. Then we are going to see the evaluation of double integral in polar coordinates, followed by the evaluation of double integral by changing the order of integration. Then we are going to see how to find the area in Cartesian coordinates by using double integration and how to find area in polar coordinates by using double integration. And at the last, we are going to see some applications of double integration in real life. Double integration is a powerful mathematical tool used to calculate volumes, areas, and other quantities in two-dimensional spaces. Double integration involves integrating a function of two variables over a two-dimensional region. Now, when we consider a function f of x comma y of two variables x and y on a finite region A, then the double integral is represented as f of x comma y dA. Now let us see what is meant by evaluation of a double integral. So there are two methods to evaluate a double integral. So in the first method, f of x comma y is first integrated with respect to y, treating x as constant between the limits a and b. And in the second method, f of x comma y is first integrated with respect to x, keeping y as constant between the limits x1 and x2, and then the resulting expression is integrated with respect to y between the limits c and d. Let us now see few examples based on double integration. Evaluate x square plus y square dA, where dA indicates small area in xy plane. First, we have to integrate the innermost integral and then we have to integrate the outer integral. So here the innermost integral is there with respect to y with the upper limit x and the lower limit 0, and the outer integral is there with respect to x with the upper limit 1 and the lower limit 0. So when we integrate this with respect to y, we will be getting it as x square y plus y cube by 3 with the upper limit x and the lower limit 0. Now we have to substitute the upper and the lower limit in the place of y. So we will be getting it as x cube plus x cube by 3 dx. Now when we integrate this with respect to x, we will be getting it as x to the power of 4 by 4 with a 4 by 3 outside. Now you substitute the upper limit 1 and the lower limit 0 in the place of x. Then we will be getting it as 4 by 3, 1 to the power of 4 divided by 4. So 4 and 4 gets cancelled. So the final answer is going to be 1 by 3 square units. So here I have given the step-by-step solution for this double integration. So this is going to be a simple example for double integration. So here in the next sum, evaluate the double integral of xy dx dy, where r is the quadrant of the circle x square plus y square equal to a square, where x is greater than or equal to 0 and y is greater than or equal to 0. So let the region of integration be the first quadrant of the circle. So here we are going to consider it as OAB. So OAB is going to be the first quadrant of the circle. And they have given it as x square plus y square equal to a square. So from that, it is evident that y is going to be equal to root of a square minus x square. So the limits of y is going to be 0 to root of a square minus x square. And for the limit of x, it is going to be 0 to a. So now when we substitute this, it is going to be 0 to a x dx, 0 to root of a square minus x square y dy. So first we have to integrate the innermost one, that is with respect to y. So it is going to be y square by 2 with the upper limit root of a square minus x square and the lower limit 0. So we have to substitute the upper limit and the lower limit in the place of y with the minus in between. Then we will be getting it as 1 by 2 x into a square minus x square. And when we integrate this with respect to x, we will be getting it as 1 by 2 a square x square by 2 minus x power 4 by 4 with an upper limit a and a lower limit 0. Now we have to apply the upper limit and the lower limit in the place of x with a minus sign in between. Then when we simplify it, we will be getting the answer as a power 4 divided by 8. So this is also an example for double integration. The third example is going to be evaluate x plus y dy dx in the region bounded by x is equal to 0, x is equal to 2 and y is equal to x. So from the question, it is evident that the limits are, for x it is going to be, the lower limit is going to be 0 and the upper limit is going to be y2, and for y the lower limit is going to be x and the upper limit is going to be x plus 2. So now first we have to integrate with the innermost integral, that is the integration with respect to y. So when we integrate x plus y with respect to y, we will be getting it as xy plus y square by 2 with x plus 2 as the upper limit and x as the lower limit. So we are going to substitute the upper and the lower limit in the place of y with a minus sign in between. Then we will be getting it as x into x plus 2 plus 1 by 2 x plus 2 the whole square minus x square by 2. If we simplify this, we will be getting it as 2x plus 2x plus 2. So take the 2 common outside. So we will be getting it as 2x plus 1 inside the integral. So when we integrate this with respect to x, we will be getting it as x square plus x with the upper limit 2 and the lower limit 0. So apply the upper and the lower limit in the place of x, and on simplification, we will be getting it as 2 into 6, which is going to be 12 is going to be the answer. So I have shown all the steps in this sum. Now the next sum is going to be evaluate integral of 0 to 2, 0 to root of 2x minus x square plus y square dy dx. So in the previous sum, we just converted the polar form into Cartesian form and then we solved it. Here we are going to convert the Cartesian form into polar form and then we are going to solve it. So here they have given the upper and the lower limit with respect to x is 2 and 0, and the upper and the lower limit with respect to y is root of 2x minus x square and 0. So now when we are converting into polar coordinates, we are going to put x is equal to r cos theta and y is equal to r sin theta. And then the upper and the lower limit with respect to theta is going to be pi by 2 and 0. And the upper and the lower limit with respect to dr is going to be 2 cos theta and 0. So when we are just converting it to the polar form, the question will be getting converted into integral of 0 to pi by 2 and 0 to 2 cos theta r square r d theta dr. So we can just represent it as r cube d theta dr. So when we integrate r cube with respect to r, we will be getting it as r to the power of 4 divided by 4 with the upper limit 2 cos theta and the lower limit 0. So we have to substitute the upper and the lower limit in the place of r with the minus sign in between. Then we will be getting it as 4 times of 4 integral of 0 to pi by 2 cos to the power of 4 theta d theta. So when we integrate this, we will be getting it as 4 into 3 pi divided by 8 into 2. So when we simplify this, we will be getting it as 3 pi by 4, which is going to be the answer. Next, we are going to see evaluation of double integral by changing the order of integration. So on changing the order of integration, the limits of integration changes. So to find the new limits, we draw a rough sketch of the region of the integration. So when some of the problems connected with double integration seems to be complicated, we can easily handle it by using this change of order of integration concept. So let us go to the first sum. Change the order of integration 0 to infinity 0 to x e to the power of minus xy y dy dx. So here the region OAB of integration is bounded by y equal to 0, that is the x-axis, and y is equal to x, which is the straight line, and x is equal to 0, that is the y-axis. A strip is drawn parallel to the y-axis, and here y varies 0 to x and x varies 0 to infinity. Now, by changing the order of integration, first we integrate with respect to y and then we reintegrate with respect to x. So, hence, integral of 0 to infinity 0 to x e to the power of minus xy y dy dx will be written as 0 to infinity y dy and y to infinity e to the power of minus xy dx. So, first when I integrate with respect to x, I will be getting it as integral of 0 to infinity y dy e to the power of minus xy divided by minus y with an upper integral infinity and a lower integral y. So when I substitute the upper and the lower integral in the place of x, I will be getting it as integral of 0 to infinity y dy divided by minus y 0 minus e to the power of y square. So now when I integrate this with respect to y, I will be getting the answer as 1 by 2 root pi. So change of order of integration plays a vital role for solving some complicated sums. Next, we are going to see how to find the area in Cartesian form using a double integration. So to find area in Cartesian form using double integration, the general formula is going to be integral of a to b integral of y1 y2 dx dy. So let us see sums based on this, which will make this concept clear. Find the area bounded by the parabola y square equal to 4ax and its lattice rectum. So as per the question, I have constructed a parabola and a lattice rectum, and now we have to find the area bounded by this parabola and the lattice rectum, that is the area ASL. Here L dash represents the lattice rectum. So the required area that we have to find is nothing but 2 times of area ASL. So as per the figure, the limits for the outer integral is going to be 0 to a, and the limits for the inner integral is going to be 0 to 2 root of ax. So now first I'm going to integrate the inner integral, that is with respect to y. So it will be given as 2 integral of 0 to a y with the upper limit 2 root ax and the lower limit 0. So when I apply the upper and the lower limit in the place of y, I will be getting it as 2 integral of 0 to a 2 root of ax dx. Now I am going to integrate this with respect to x. Then I will be getting it as 4 root of a x cube x 3 by 2 divided by 3 by 2 with the upper limit a and the lower limit 0. When I substitute the upper and the lower limit in the place of x, I will be getting the answer of 8a square by 3. So by constructing the diagram properly, we can solve this sum easily. So in this next question, we are going to find the area enclosed by the pair of curves y is equal to 2 minus x and y square is equal to 2 into 2 minus x by using the concept of double integration. So here they have given two equations, y equal to 2 minus x and y square is equal to 2 into 2 minus x. So by solving these two equations, we are getting the 2 points of intersections 0, 2 and 2, 0. So now by using the double integration concept, the required area is going to be integral of 0 to 2 dx and integral of 2 minus x root of 2 into 2 minus x dy. Now first we are going to integrate with respect to y, then we will be getting it as integral of 0 to 2 dx y with an upper limit root of 2 into 2 minus x and a lower limit 2 minus y. So we have to substitute the upper and the lower limit in the place of y. Then we will be getting it as integral of 0 to 2 dx root of 4 minus 2x minus 2 plus x. Now again we are going to integrate this with respect to x. Then if we integrate this with respect to x, we will be getting it as minus 1 by 3 4 minus 2x to the power of 3 by 2 minus 2x plus x square by 2. Now we have to apply the upper limit 2 and the lower limit 0 in the place of x. Then we will be getting the final answer as 2 by 3. So here I have shown the step-by-step solution for this sum and the diagram with respect to the question. Next, we are going to see how to find area using the concept of double integration for polar coordinates. So for this, the formula is going to be area equal to double integral of r d theta dr. So now let us solve a sum based on this concept. Find by double integration the area lying inside the cardioid r equal to a 1 plus cos theta and outside the circle r equal to a. So the given two equations are r equal to a into 1 plus cos theta and r equal to a. So let this be the upper and the lower limit for r. So to find the upper and the lower limits for theta, let us solve both the equations by eliminating r. Then we will be getting a into 1 plus cos theta equal to a. From this, it is evident that cos theta is equal to 0. Therefore, theta is going to be minus 1 by 2 or pi by 2. So, which we can consider as the upper and the lower limit. Now, we are getting the equation as integral of minus pi by 2 to pi by 2 and integral of a to a into 1 plus cos theta r d theta dr. So, first we are going to integrate the innermost integral, that is the integral with respect to r. So, when we integrate r, we will be getting it as r squared by 2 with the lower limit a and the upper limit a into 1 plus cos theta. So, we have to apply the upper and the lower limit in the place of r with the minus sign in between. Then we will be getting an equation as a square by 2 integral of minus pi by 2 to pi by 2 cos square theta plus 2 cos theta d theta. So when we integrate this with respect to d theta, we will be getting an answer as a square integral of 0 to pi by 2 cos square theta plus 2 cos theta d theta. So when we integrate this with respect to d theta and simplify it, we will be getting it as a square pi by 4 plus 2 into sine theta pi by 2 0 to pi by 2, and when we simplify this we will be getting it as a square pi by 4 plus 2, which is nothing but a square by 4 pi by 8, pi plus 8. So here I have shown step by step simplification. The last section of this module is going to be applications of double integration. So as I said before, double integration plays a vital role in calculating volumes, surface areas, masses and moments of inertia. So it is useful for calculating the volume of a solid bounded by a surface. It helps in finding the area of a two-dimensional region, and it also helps in determining the mass of a thin plate with varying density. Certain main applications of double integration is physics is that it helps to calculate the heat flow across a surface. It is used to analyze fluid flow and pressure distribution, and it also aids in computing electromagnetic fields and forces. The three main applications of double integration in engineering is that it helps in structural analysis, fluid mechanics, and also it is very helpful in control systems. In economics, double integration calculates the total benefit consumers receive from a good or service. It determines the total benefit producers receive from selling their products, and it is also used to analyze the equilibrium price and quantity in a market. In biology, double integration models are used to find the diffusion of molecules within cells and tissues. It is used to analyze the growth and distribution of populations, and it also helps to understand the dynamics of species evolution and adaptation. So this is going to be the end of the module. Thank you, students. Let us connect again in the next interesting topic. Thank you.